Welcome back to a new video about Chebyshev response filters. This is our example number 4. In this example we will discuss the bandpass filter design using LC ladder configuration. We will work out our calculations step by step and also verify these in SPICE simulations. So this is our example. We have the objective: design a Chebyshev response bandstop filter. It must have an LC ladder configuration. We will see that shortly what it means. And we need to use 50 ohm double terminated shunt input circuit. Now looking at this circuit block diagram first, this is a generalized filter where we need to design our band stop filter. The RS, which is the source resistor, and the RL, which is the load resistor, are normalized to 1 ohm here. So we need to scale it up later to 50 ohm. That is actually the meaning of this last sentence. The specifications for this bandstop filter design is the maximum passband ripple a max of 1 dB. That means for the Chebyshev response, the ripple table where we need to look at is also 1 dB. The minimum stop band attenuation is 25 dB, and the lower passband frequency must be 100 kHz. The upper passband frequency must be 900 kHz, and also the stop band frequency and the upper and lower than the upper is given. That's 200 kHz and 500 kHz. So let's look at our solutions for this design. We start with the step 1, which is the passband bandwidth, so the omega BW, and also the center frequency omega center. Now we know the omega bandwidth is the difference between the upper and the higher, the lower, upper and the lower passband frequency, which is 900 kHz minus 100 kHz, which is then 800 kHz. But given in the omegas, we need to multiply it by 2 pi. So you will get now this calculation, which will then be 16 times 10 to the power 5 pi radians per second. The center frequency is also called the resonance frequency, is the geometric mean of the upper and the lower passband frequency, which is then given by this expression. And we now again convert this upper and the lower passband frequencies in radians per second. Just multiply each of them by 2 pi and you get this expression. Now you get now 1.885 mega radians per second, or million radians per second. That's step 1. Step 2 is the normalized passband frequency and the normalized stop band frequency of the prototype low pass filter. So we actually start with the prototype low pass filter. We determine there the values and we transform our circuit later in the band stop filter. Normalized passband frequency is given by this expression for the band stop filter design. So the omega bandwidth divided by the difference between the upper and the lower, but that's just 1, of course, because this is also the same as the numerator. And the stop band, normalized stop band frequency is also similar to that, but then in the denominator you get now the upper stop band frequency and the lower stop band frequency. Now when you do that, you get now 2.76. The step 3 is the filter order of the prototype low pass filter. Now for that we need to calculate this coefficients epsilon p, which is related to a max. We know what a max is, which is 1, so you get now 0.5088. Epsilon s, which is related to a minimum, a min, and that is then 25. You get now 17.755 approximately. Taking this together, and this is the formula for calculating the order of a Chebyshev response filters. This is now what you have here. When you now substitute the given values for the what we have calculated in step 2 for omega p and omega s, and what we have just calculated for epsilon p and epsilon s, you now get 2.5936. But we need to use integer orders, so you cannot go actually to second order because that is not sufficient. So we need to go to a third order. So we need to design a third order Chebyshev response filter. The next step is step 4, this band stop bandwidth scaling factor, KFBS, which is actually just the bandwidth we have determined already in step 1. So this is just 16 times 10 to the power 5 pi radians per second. Now moving on, and that's of course 800 kilohertz. Now taking everything together, this is the order we have determined. These are the omega center, omega bandwidth, and also our band stop bandwidth scaling factor, and also our magnitude gain scaling factor, because we need to go from 1 ohm to 50 ohm. So Km, which is the magnitude scaling factor, must be 50. This is a table for the 3rd order, 5th order, and 7th order Chebyshev response 1 dB ripple for LC ladder low pass normalized element value. So it is still low pass, but we need to transform that shortly to a band stop filter. And we need this row here actually. You see the coefficients here, x1, x2, and x3. Those are the values of the components in this prototype low pass filter. This is the low pass filter. C1 is here now 2.0236 farads. L2 is here 0.9941 henries. And also C3 is the exact same as C1. So you see actually the coefficient, but that needs to be used as a coefficient to the actual band stop filter. Now what is now the transformation from the low pass to band stop filter? Now you replace your capacitors, so your capacitor here, by a series of an inductor and a capacitor. And when you see an inductor, you replace that by a parallel of an inductor and a capacitor. This is actually the reverse of what we did in the bandpass filter design. There we replaced the capacitor to a parallel combination of an inductor and a capacitor, and the inductor was replaced by a series combination of an inductor and a capacitor. So okay, now moving on, what is then the circuit we will get? Now this will be a series combination, you see that here. This will be also a series combination, and this will be L2 will be a parallel combination. And also the RS and RL will be scaled up to the value we wanted, so by the magnitude scaling factor RS prime and RL prime. So the complete circuit is now given. Of course we need to determine the value, so let's also continue with that one. This is now the circuit we need to work it out, and this is now the second of the sixth step, step 6. So the CS1, which is the series first capacitor, is calculated using this formula. Now we get actually using the C1 from the table. This is what we have determined, 16 times 10 to the power 5 pi radians per second, which is shown here. The Km is 50 and the omega center is also shown here. So this is just substitute the values here. And a similar form you get LS1, these are the formulas. And now for CP1 and LP1, also everything is actually known, so you just actually substitute the values you have. And a CS2 and also the LS2 are the exact same as the CS1 and LS1, because the coefficients for X1 and X3 are the exact same. The RS and RS prime and RL prime are of course 50 as discussed, so that's also known. So we have now the 8 components we wanted here all determined. Now let's now look at the design circuit now in the SPICE simulator. This is the prototype circuit. You see that low pass prototype third order. This is now the design third order Chebyshev response LC ladder band stop filter. You see the values and also the values for the other RS and RL. Okay, let's now look at the simulation result and check that this is indeed doing the job. This is now the magnitude response of the body plot. You see a couple of data here, so let's label them one by one. The passband gain is here, which is that a lower frequency at DC is minus 6.02 dB. And also at high frequency is also minus 6.02 dB. Why? Because at the passband gain, at very low frequencies and very high frequencies, the filter is actually considered to be as actually unity gain. So you get actually 50 ohm over 50 plus 50, which is then 50 over 100, which is 1 over 2. 20 log of 1 over 2 is minus 6.02 dB approximately. The next one is a lower passband frequency at 100 kHz, which is actually shown here, and that goes down here by 1 dB, because this was minus 6.02 dB, you go to minus 7.02 dB, which is 1 dB ripple, so that's as required. The upper one is here, again, minus 7.02 dB, so again 1 dB down from the high frequency gain at 900 kHz, so again as required. The lower stop band frequency is shown here, which is going down from minus 6.02 dB all the way to minus 41.85 dB at 200 kHz. That 35.483 dB down, that is definitely sufficient, because we need to have a 25 dB minimum. So at 500 kHz, you see that here, that's the upper stop band frequency, that goes down to minus 34.96 dB, which is actually a decrease of 28.97 dB, which is also sufficient because we need to have a minimum of 25. But you see in this case that this is not symmetric, so it's not that this value, the decrease in the gain here, is not the same as the decrease in the upper stop band frequency. But it is sufficient, so that is actually definitely minimum what we wanted. The center frequency is also shown here, which is approximately 300 kHz, so 299.984 kHz. So we can say all the specifications are met, so we have actually achieved our goal. Alright, this is our example number 4 about the Chebyshev response bandstop filter design using the LC ladder configuration. If you have any questions, comments, please let me know. I'll try to answer them as soon as possible. See you next time in another video. Take care.